Hello everyone. So to build a three-layer deep neural network for nonlinear regression, we use NumPy and we have 7 steps in total. So the first one would be the initialization where we define the architecture and initialize the parameters or weights of the network and also the biases for the each layer, and the network will have two hidden layers and one output layer. And the next one is the activation function where we implement non-linear activation functions, and for this particular network we will use ReLU, rectified linear unit, for hidden layers because of its simplicity. So ReLU will be used for the hidden layers, and since it is a regression problem, no activation will be used for the output layer. So the third one would be the loss function, where we use the loss function that we use is the mean squared error (MSE) as the uh, loss function to measure how well the model performs. And the next one would be the forward propagation and backward propagation, where we implement forward propagation to compute the network's predictions, and we implement the backward propagation to compute gradients of the loss function with respect to the parameters. And also the forward propagation will calculate the output of the network layer by layer, and the backward propagation calculates the gradients of the loss with respect to each parameter. And then this is our synthetic data generation, and this is our model training, and this is the final loss, and this is the loss curve. So the we also do the parameter updating after each uh, run, and update the weights and biases based on the gradients calculated from backward propagation using the learning rate. And also the training loop that we ran here, it combines all the above steps into a training loop that iterates over a number of epochs, that is in our case 1000. uh, so let's look at this loss curve, and as we know, the network was trained for 1000 epochs, and the loss significantly decreased over time, indicating the model was learning from the data. The final loss after 1000 epochs was approximately 0.0192, and showing that the model's predictions became quite close to the true values. The plot of the loss curve demonstrates how the loss decreases steadily, indicating that the model was effectively minimizing the error between its predictions and actual data points. And this steady decrease is a good sign of learning without overfitting and underfitting significantly. So let's move to the next part. Here we create a three-layer deep neural network for non-linear regression in PyTorch without using the built-in uh, NN.linear functionality, and uh, it involves defining the weight matrices and biases manually, implementing the forward pass, and leveraging PyTorch's automatic differentiation for the backward pass. And also, we will use PyTorch tensor operations to manually perform the matrix multiplications and addition of biases. So we'll follow the steps. Firstly, we define the model and manually define the layers with their weights and biases, and then we get the data, and also we use the activation function, which is same, the ReLU, and the loss function is mean squared error, and the forward and backward passes, uh, we implement the forward pass manually, and backward pass and optimization, we for that we utilize PyTorch's AutoGrad to automatically compute gradients, and an optimizer to update the model's performance. And this code defines a three-layer neural network without using the PyTorch's built-in function and performing the matrix multiplications and bias additions manually. The forward method computes the output of the network, and touch.relu is used as the activation function, and the MSE loss function calculates the loss. PyTorch automatically computes the gradients for these operations, and the SGD optimizer uh, updates the model's weights and biases. And yeah, this 3D plot, it visually represents the true data points alongside the model's predictions. So the blue ones are the true data and model predictions are the red ones. So it is pretty accurate. So let's move to the next one. Here we implement a three-layer deep neural network for the nonlinear regression using PyTorch's built-in functionality. And for this we will leverage torch.nn modules like this for the layer definitions, and we use PyTorch automatic differentiation for back propagations. These are the following steps. Firstly, we define the neural network class. This is the three-layer net. Um, And for this, we use the NN dot module to define our network architecture with three layers. And the activation function, we are using the ReLU, rectified linear unit, for hidden layers to introduce non-linearity. And the loss function is the same, the mean squared error. A mean squared error will be used as it is suitable for regression tasks, and the optimizer to update the network's weights based on the calculated gradients, we use the optimizer. And the training loop, we implement the loop where the model will learn from the data over multiple epochs, and the network architecture is defined um, with relayer net using ReLU activation functions between layers for non-linearity and a linear layer at the end of the output. The model's parameters are updated using gradient descent based on the MSE loss between the predicted and true values. Uh, the plot, uh, this demonstrates the training loss over epochs for the three-layer neural network trained on the synthetic data that we have generated. And ideally, you would see a downward trend in the plot, indicating that the network is learning from the data over time and the loss is decreasing. So these are the epochs. Yeah. So let's move to the next one. Yeah, here we implement a three-layer deep neural network for non-linear regression using PyTorch Lightning. We'll follow a similar structure as we would with the plain PyTorch, but here we leverage the additional abstraction and functionalities provided by PyTorch Lightning. PyTorch Lightning simplifies a lot of code, especially around training loops, validation, and testing. First, let's just ensure that the PyTorch Lightning is installed in our environment. Then we define a neural network model with three linear layers and ReLU activations extending PL dot lightning module, and implement the forward method to define how the forward pass is computed using the training step method to tell PyTorch Lightning how to perform a training step, including how to calculate the losses. And then we configure an optimizer. In the configure optimizers method, it should be yeah, it's here. And then we prepare the data using PyTorch data loader, just like this, the data loader, and the tensor data set suitable for training. And then we initiate a model instance and uses PyTorch, which uses PyTorch Lightning Trainer to train the model over specified epochs, simplifying the training loop and the other code. And the PyTorch Lightning handles much of the routine work for us, like moving tensors to correct the device, so you don't have to manually transfer data between CPU and GPU. And this makes the code cleaner and more focused on the model's architecture and the training logic. So let's go to the next one. Here we create a TensorFlow model from scratch without using any high-level APIs, and we will implement a three-layer deep neural network for non-linear regression. And the model will be trained with a synthetic data set similar to the one we described so far. And this defines a neural network with three layers, including the ReLU activation functions for hidden layers and a mean squared error loss function and a training function that uses gradient descent to update the weights and biases. We also generate synthetic data for the we also generate the synthetic data for uh, training the model and shuffle and batch it using a tf.data.data set. Yeah, we have used it shuffling and batch the data set. And after training the model, you can compile the training function using the tf dot function to speed up the execution by converting it into a static graph. So here we initialize the weights and biases, and then forward function, loss function, training function, and the loop, training loop. And then this is the tf dot. Here we utilize the tf dot function to speed up the execution by converting it into a static graph, and then we plot. We use a scatter plot. So the next one would be here we create a three-layer neural network for nonlinear regression using TensorFlow's built-in layers. We will use the tf.keras API, which provides a lot of built-in layers and functionalities such as activation functions, loss functions, and optimizers. The code that this sets up the model with Keras functional API and trains it using a synthetic dataset similar to the previous example. So here we define the model using the functional API and then optimizer and loss functions, training loop, and then evaluation of the model. This is the plotting. So the next one would be here we will create a similar three-layer deep neural network for nonlinear regression, and this model will be trained on synthetic dataset that will generate similar to the previous examples. Here the code, this code is to create and train the model using TensorFlow functional API, and then the script creates a tf.keras model using functional API. It sets up a model with two hidden layers and uh, two hidden layers of dense units with ReLU activation functions, ReLU activation functions, and a single output unit without activation. uh, this is for regression, and we compile the model with the Adam optimizer and mean squared error loss. The model is then trained with the fit method on our synthetic data set. Finally, we plot the features colored by the model's predictions. Yeah, so this is the 3D plot for it. So this is an example of how you can use TensorFlow's high-level Keras API to build, train, and evaluate a simple neural network on the MNIST dataset, which is a collection of handwritten digits. We will then visualize the results with a confusion matrix. And then for this, we first load and preprocess the MNIST dataset. Then we define a simple then we normalize the data, and then we define a simple neural network with two dense layers. We compile the model with the Adam optimizer and sparse categorical cross entropy loss function. After training for 5 epochs, we evaluate and print the accuracy on the test set. And then finally, we use the trained model to predict classes for the test set, and compute a confusion matrix, which we visualize using the Seaborn's um, heat map function. So we repeat the same what we have done so far with using JAX. So this is an firstly, we ensure that we have installed the all the necessary libraries, and then this is in example using JAX and Flax library to create a simple neural network similar to the TensorFlow example. And then it is important to note that JAX operates differently than TensorFlow and requires different coding patterns. Um, this code uses the Flax library to define a simple feed-forward here we are using all the Flax library to define a simple feed for a neural network. It initializes the parameters and sets up the optimizer. The train step function, yeah, the train step function performs a single step of training using JAX's automatic differentiation and JIT compilation for performance. And yeah, here it is. And this train step function performs a single step of training using the JAX automatic differentiation and JIT compilation for performance. And the training loop runs for 5 epochs. The training loop runs for 5 epochs and updating the parameters with gradients computed from the mini batch of the data. And then finally, we evaluate the model using the test data and then compute the confusion matrix using scikit-learn and visualize it with the Seaborn. So yeah, that's about this assignment.